Preparing for a machine learning engineer interview? You've reached Candy Mentor, and this video is for you. We'll walk through 20 key questions you're likely to face. For each question, you'll see a sample answer followed by the key points to cover. Subscribe, like, and share, and drop a topic request in the comments. Question 1. How do you detect and reduce overfitting in a machine learning model? Overfitting means the model learns noise instead of the underlying pattern. I diagnose it by comparing train and validation performance. High train accuracy with poor validation is the classic signal. To reduce it, I use simpler models, regularization, more data, augmentation, early stopping, dropout, or cross-validation. I also check leakage, because it can look like great training performance but fail in production. The goal is generalization, not memorization. While answering, focus on train validation gap, model complexity, regularization, cross-validation, early stopping, data augmentation, leakage checks, and why production generalization matters more than training accuracy. Question 2. What is the bias-variance trade-off, and how does it affect model selection? Bias is error from overly simple assumptions. Variance is error from sensitivity to training data. A high bias model underfits, like linear regression on a nonlinear problem. A high variance model overfits, like a deep tree memorizing noise. In practice, I compare validation performance, tune complexity, regularize, and use ensembles when appropriate. Model selection is about finding the lowest validation error, not the most sophisticated algorithm. Make sure to cover underfitting versus overfitting, error decomposition, model complexity, training and validation behavior, examples like linear models versus trees, and practical ways to balance both. Question 3. How would you handle an imbalanced classification problem? The first step is choosing the right metric. Accuracy is often misleading when one class dominates, so I look at precision, recall, F1, PRAUC, and business cost. Then I try class weights, oversampling, undersampling, or synthetic methods like SMOT. I keep validation and test sets close to real production distribution. Finally, I tune the decision threshold based on whether false positives or false negatives are more expensive. In your answer, talk about metric choice, class weights, resampling, threshold tuning, stratified splits, cost-sensitive learning, precision recall trade-offs, and validating performance on realistic class distributions. Question 4. Explain data leakage and give examples of how it can happen. Data leakage happens when training uses information that would not be available at prediction time. For example, using a feature like refund process to predict future churn leaks the answer. Another common case is scaling or imputing before splitting, which lets test statistics influence training. In time series problems, random splits can leak future information. I prevent leakage with time-aware splits, feature availability checks, and pre-processing fitted only on training data. Be sure to mention target leakage, train test contamination, time-based leakage, pre-processing before splitting, duplicate records, feature availability at prediction time, and prevention using proper pipeline design. Question 5. How do you choose the right evaluation metric for a model? I start from the business decision the model supports. For balanced classification, accuracy may be acceptable. For fraud or medical detection, recall or precision recall AUC is usually better. For regression, I choose MAE when errors should be treated linearly, and RMSE when large errors matter more. For ranking, I use NDCG or MAP. I also monitor secondary metrics, because optimizing one number can create bad product behavior. While answering, connect metrics to business objectives, regression versus classification, class imbalance, ranking problems, calibration, threshold-dependent metrics, and why one headline metric is rarely enough. Question 6. What is cross-validation, and when would you avoid standard k-fold cross-validation? Cross-validation estimates model performance by training on multiple splits and averaging validation results. It is useful when data is limited, because every example gets used for validation once. I avoid standard random k-fold when data has time order, user grouping, or duplicates, because it can leak information across folds. For those cases, I use time series splits, group k-fold, or stratified k-fold. The split strategy must match production reality. Make sure to cover k-fold mechanics, variance reduction in evaluation, hyperparameter tuning, stratified folds, grouped data, time series data, leakage risks, and computational trade-offs. Question 7. How would you design a machine learning pipeline from raw data to production predictions? I design the pipeline as a reproducible system, not a notebook. Raw data is ingested, validated, transformed into features, and versioned. Training jobs log parameters, metrics, code version, and artifacts. Approved models move to a registry, then deploy through batch, real-time, or streaming serving, depending on latency needs. After launch, I monitor data quality, drift, latency, and business metrics. Retraining is triggered by schedule, drift, or performance degradation. In your answer, include data ingestion, validation, feature engineering, training, experiment tracking, model registry, deployment, monitoring, retraining, reproducibility, and separation between offline training and online serving. Question 8. What is the difference between batch inference and real-time inference? Batch inference generates predictions on a schedule, like scoring all users every night for churn risk. It is simpler, cheaper, and handles high throughput well, but predictions may be stale. Real-time inference responds per request, often within milliseconds, so it is better for recommendations, fraud detection, or personalization. It needs low latency serving, scaling, and stronger reliability. Many systems use a hybrid approach: batch pre-compute candidates, then real-time rank them. Be sure to discuss latency requirements, throughput, cost, infrastructure complexity, freshness of predictions, use cases, failure modes, monitoring, and when hybrid serving architectures are useful. Question 9. How do you monitor a machine learning model after deployment? I monitor both software and ML behavior. Software metrics include latency, availability, memory, CPU, and error rate. ML metrics include feature distributions, missing values, prediction distribution, drift, calibration, and performance once labels arrive. If labels are delayed, I use proxy metrics and business KPIs. I set alerts for meaningful deviations, not noise. A strong deployment also has model versioning, shadow tests, canary rollout, and rollback capability. While answering, cover model performance, data drift, concept drift, feature quality, prediction distributions, latency, error rates, delayed labels, alerting thresholds, dashboards, and rollback strategies. Question 10. What is feature engineering, and how do you decide which features to create? Feature engineering turns raw signals into representations a model can learn from. I create features based on domain logic, exploratory analysis, and model needs. Aggregations, ratios, time window counts, categorical encodings, text embeddings, or interaction terms. I validate that every feature is available at prediction time to avoid leakage. Then I measure impact through cross-validation or online experiments. Good features often beat switching to a more complex model. Make sure to mention domain knowledge, transformations, aggregations, encodings, time windows, interaction features, leakage prevention, feature importance, experimentation, and keeping training serving logic consistent. Question 11. How do you handle missing values in a dataset? I first understand why values are missing. Missing completely at random is different from missing because a user skipped a field or a sensor failed. For simple cases, I use median, mode, or constant imputation, often with a missing indicator feature. For more complex cases, I may use model-based imputation. I avoid fitting imputers on the full dataset before splitting. Sometimes missingness itself is predictive, so I preserve that signal. In your answer, talk about missingness patterns, deletion versus imputation, mean or median imputation, model-based imputation, missing indicators, domain meaning, and fitting imputers only on training data. Question 12. Explain precision, recall, F1 score, and when you would prioritize each. Precision asks, of the items I predicted positive, how many were correct? Recall asks, of all true positives, how many did I catch? F1 is their harmonic mean, useful when I need a balance. I prioritize precision when false positives are costly, like blocking legitimate payments. I prioritize recall when missing positives is dangerous, like disease screening. The threshold should be tuned based on business cost, not left at 0.5 automatically. Be sure to define each metric clearly. Connect them to false positives and false negatives. Discuss threshold tuning, imbalanced data, business costs, and examples like fraud or spam detection. Question 13. What is regularization, and how do L1 and L2 regularization differ? Regularization adds a penalty to discourage overly complex models. L1 regularization penalizes absolute weight values, which can drive some coefficients exactly to zero, making it useful for feature selection. L2 penalizes squared weights, shrinking them smoothly, but usually not to zero. The regularization strength controls the trade-off between fit and simplicity. In practice, I tune it with validation data because too much regularization causes underfitting. While answering, cover penalty terms, controlling model complexity, overfitting reduction, L1 creating sparsity, L2 shrinking weights smoothly, hyperparameter strength, and examples in linear models or neural networks. Question 14. How would you explain gradient descent to a non-ML engineer? Gradient descent is a method for optimizing a function. Imagine you're trying to find the lowest point in a hilly landscape. You start at a random spot and take small steps downhill. Each step is guided by the slope you're on. In machine learning, we use this idea to adjust the weights of a model to minimize errors. Each iteration reduces error, and over time, the model converges on the best solution. Gradient descent is an iterative way to minimize error. Imagine standing on a hill in fog and taking small steps downhill based on the slope under your feet. In ML, the hill is the loss function, and the slope is the gradient. The learning rate controls step size. Too large can overshoot, too small is slow. Mini-batch gradient descent and Atom make this process more efficient for large models. Make sure to describe the objective function, gradients as direction of steepest increase, learning rate, iterative updates, convergence, local minima, and practical variance like mini-batch or Atom. Question 15. How do you decide between using a simple model and a complex model? I start with the simplest strong baseline because it gives a performance floor and is easier to debug. If logistic regression or gradient boosting meets the business requirement, I may not need a deep model. I move to complexity when data volume, feature type, or accuracy targets justify it. I compare validation performance, latency, interpretability, maintenance cost, and failure modes. A complex model must earn its place with measurable lift. In your answer, discuss baseline models, interpretability, data size, latency, maintainability, performance lift, regulatory constraints, debugging, deployment cost, and proving complexity through validation or experiments. Question 16. What is model calibration and why does it matter? Calibration means predicted probabilities match real-world frequencies. If a model assigns 0.8 probability to many cases, about 80% of them should be positive. This matters when decisions depend on risk, like lending, fraud review, or medical triage. A model can be accurate but poorly calibrated. I check reliability curves and Breyer score, then apply Platt scaling or isotonic regression if needed. Calibration should be evaluated on held-out data. Be sure to cover predicted probabilities, calibration curves, reliability diagrams, Breyer score, threshold-based decisions, risk ranking, Platt scaling, isotonic regression, and why accuracy alone is insufficient. Question 17. How do you make ML experiments reproducible? Reproducibility requires controlling every input to training. I version the dataset, feature definitions, code, configuration, dependencies, and model artifacts. I log random seeds, hyperparameters, metrics, and evaluation splits in an experiment tracker. Containerized environments help avoid dependency drift. For distributed training, I document any non-deterministic behavior. The key is that another engineer should be able to rerun the experiment and get comparable results. While answering, mention versioning data, code, features, configurations, random seeds, environments, dependencies, model artifacts, experiment tracking tools, deterministic pipelines, and documenting evaluation splits. Question 18. What is concept drift, and how would you respond to it in production? Concept drift happens when the relationship between features and target changes. For example, fraud patterns change after attackers learn the detection rules. Data drift only means input distributions changed. Concept drift means the model's learned mapping is becoming wrong. I monitor performance on fresh labeled data, plus proxy business metrics when labels lag. Responses include retraining, adding new features, shortening training windows, or rolling back. Any update should be validated before rollout. Make sure to distinguish concept drift from data drift. Describe changing input-output relationships, monitoring with delayed labels, retraining strategies, alerting, model comparison, and safe rollout practices. Question 19. How would you build a recommendation system for an e-commerce product? I would split the system into candidate generation and ranking. Candidate generation retrieves a few hundred relevant items using collaborative filtering, embeddings, popularity, or content similarity. The ranker then scores candidates using user behavior, item features, context, price, freshness, and business constraints. For cold start, I use popularity and content-based features. I evaluate offline with NDCG or recall, but final success comes from online metrics like conversion, revenue, and retention. In your answer, cover candidate generation, ranking, collaborative filtering, content-based features, embeddings, cold start, offline metrics, online A/B testing, latency constraints, and feedback loops. Question 20. How do you approach deploying a new model safely without hurting users? I avoid big bang model launches. First, I validate offline on representative data and check slices, latency, fairness, and failure cases. Then I may run shadow mode, where the model predicts without affecting users. Next comes a canary release or A/B test with guardrail metrics, like errors, latency, complaints, and revenue impact. If metrics degrade, rollback must be easy. Safe deployment is an engineering process, not just a model score. Be sure to mention offline validation, shadow deployment, canary release, A/B testing, monitoring, rollback, model versioning, guardrail metrics, fairness checks, and collaboration with product and engineering teams. If you are still with us, congratulations. You are much ahead of the rest and serious about preparing for your interview. We hope we were able to add value to your preparation and create some helpful content. Do not forget to like and share this video. Your small act can do great things for us.